Welcome to the Explainer. Got an exam on natural language processing coming up? Then you know it's all about getting that end-to-end process down cold. Well, you're in the right place. Today, we're going to walk through the entire NLP pipeline step by step. We'll hit all the key concepts and comparisons you absolutely need to know to ace those questions. So, let's get right into it.
So really, everything in NLP boils down to this one big question, right? How in the world do we get a computer, a machine, to actually understand what we're saying? The whole pipeline we're about to cover is the answer. It's the journey of taking our messy human language and turning it into clean, structured data that a computer can finally understand and work with.
And here it is. This is our roadmap for today. We're just going to follow this process from beginning to end. Honestly, if you're in an exam and you get a question about the NLP process, just picture this flowchart in your head. It's the perfect way to structure your answer and show that you really get the big picture.
We're going to break this down into 5 key stages. First up, cleaning the text. Then, turning those words into numbers. After that, we'll figure out which of those numbers are actually worth paying attention to. Then we'll look at a really cool application, finding hidden topics. And we'll wrap up by learning how to make a machine tell us how similar 2 pieces of text are. Okay, let's dive into section 1. We're starting right at the beginning with pre-processing. Before you can even think about cool stuff like AI models, you have to get your hands dirty and clean up the raw text. This is the foundational step, and if you mess this up, everything that comes after it is going to have problems. So every NLP project in existence starts with something just like this, a simple string of text. Our job is to make this thing, the sentence, make sense to a machine.
And the very first thing we have to do is break it down. Think of it like taking apart a Lego set. We have to separate all the individual bricks. This process is called tokenization, and it's basically the gateway to everything else. Without it, the computer just sees a random jumble of letters.
And here's what you get. See? It's not one string anymore. It's a list of individual items. These are our tokens that the machine can now look out one by one. And hey, notice something important here. Even the exclamation mark is its own token. How you handle punctuation is a big decision you have to make right at the start.
All right, pay attention here because this is a classic exam question. Stemming versus lemmatization. Stemming is the quick and dirty method. It just hacks off the end of a word. It's fast, yeah, but you can end up with nonsense words. Lemmatization, on the other hand, is the brainy approach. It actually uses a dictionary to figure out the word's true root form. So the key thing you have to remember for the test is the trade-off. Stemming is fast but sloppy. Lemmatization is slow but accurate.
Okay, on to the next stage. We've got our clean tokens, but computers don't speak English, right? They speak math. So now we have to figure out how to turn these words into numbers.
The most basic way to do this is something called bag of words. Literally, just imagine throwing all the words from your text into a big bag, shaking it up, and then just counting how many times each word appears. It's super simple, super fast, but you lose all the grammar and word order. Now, a much smarter approach is TF-IDF. This doesn't just count words, it actually weighs them. The idea is that if a word shows up a lot in one document, that's a high term frequency, but is pretty rare across all the other documents, a high inverse document frequency, then that word is probably really important. It's a great way to automatically filter out boring, common words like the, or is.
So TF-IDF is cool, but it still kind of treats words as separate things. But what if we could capture the meaning of words in our numbers? Well, that's where word embeddings come in. These things are amazing. They turn words into these dense vectors, where words with similar meanings are mathematically close to each other. And this equation here is the classic example that proves it works. You can literally take the vector for king, subtract the vector for man, add the vector for woman, and the result is incredibly close to the vector for queen. You're doing algebra on concepts. It's wild.
So how do we make these incredible embeddings? Well, a famous algorithm for this is word-to-vec, and it has 2 main flavors you see here. Skipgram on the left takes one word and tries to predict the words around it. This makes it really good for learning the meaning of rare words. Then you have SIBO on the right, which stands for continuous bag of words. It does the exact opposite. It looks at a bunch of context words to predict the one in the middle. SIBO is usually faster and better for words that appear a lot. Another classic trade-off you'll want to remember.
So we've turned our text into a whole bunch of numbers. But here's the thing. Not all of those numbers or features are actually useful. A lot of them are just noise. So the next critical step is to pick out the most important ones. This makes our models faster and usually more accurate. And this table is a perfect cheat sheet for an exam. You've got 3 main ways to do this. Filter methods are the fast and cheap option. They just use stats to rank features. Wrapper methods are the opposite. They're slow and expensive because they literally try out different feature combinations with your model, but they're super accurate. And then embedded methods are that nice middle ground where the feature selection is baked right into the model's training process itself.
Okay, so our text is prepped, turned into numbers, and we've picked the best features. Now what? Well, let's look at a really powerful thing we can do with all this work, automatically discovering the hidden themes or topics inside a giant pile of documents.
Hey, look, it's our roadmap again. The process for topic modeling is pretty similar. We gather and pre-process our text, then we pick an algorithm. A super common one is called latent Dirichlet allocation, or LDA. We let it run, and then comes the fun part, interpreting the topics it discovers.
So what's the big idea behind LDA? It's actually pretty simple when you think about it. It just assumes 2 things. First, that every document is made up of a mix of different topics. And second, that every topic is made up of a mix of different words. LDA's job is to look at all the text and basically work backwards to figure out what those secret hidden topics must have been.
And this is what the output looks like. The model won't spit out a nice label like pets, cats. It's not that smart. It'll just give you a list of words, a cluster. It's our job as humans to look at words like cats, milk, and cute, and say, okay, that topic is clearly about cats. And it can also tell us that a single document, like one about cats and dogs, is a 50-50 mix of both topics. All right, let's head into our final section. Now that we have these nice numerical representations of our text, we can do some really useful math with them. Like for instance, we can calculate exactly how similar 2 documents are. Think about how useful that is for things like search engines or checking for plagiarism.
Cosine similarity is a real workhorse here. The cool thing about it is that it doesn't care how long the documents are, it only cares about the angle between their vectors in that high-dimensional space. If the angle is 0, that means they're pointing in the exact same direction, and the similarity is a perfect 1. If they're at a 90-degree angle, totally unrelated, the similarity is 0.
Now, Jacquard's similarity takes a different approach. It's much simpler. It just looks at the unique words in 2 documents and asks a basic question. What percentage of the total words are shared between them? It's really intuitive and works great when you're just comparing simple sets of keywords.
And here is the big exam takeaway. When do you use which one? It's all about picking the right tool for the job. If you're comparing long documents and the frequency of the words matters, like with those TF-ID vectors we talked about, you're going to use cosine similarity. But if you're comparing something short, like tags on a video, and you just care if a word is there or not, then Jacquard's similarity is your best bet.
And that's the whole pipeline, from start to finish. Every single step we just walked through, from chopping up a sentence into tokens to calculating the angle between vectors, is a crucial building block for all the modern AI we use every day. We've managed to turn messy human language into cold, hard logic. So it kind of leaves you with a big question, doesn't it? Now that the machines can read, what should we teach them to do next?